everyone. Today we are going to be talking about calculating gravitational potential energy, or GPE. So consider that you have an object that is being held above the surface of the Earth. We know that if we release this object, it will fall to the surface of the Earth. And the reason that that happens is because the object has gravitational potential energy, and that is what we're going to be diving into a little bit more today. Okay, so we know about work. Work is a force times a displacement. Now in this case, the displacement is how high that object is above the surface of the Earth, which we will call its height. So what about the force? Well, this force is going to be the force due to gravity. And we know, thanks to Newton, that the equation for this force is Gmm over r squared. Now in this case, the g is the universal gravitational constant, big M is the mass of the Earth, and little m is the mass of the object. And r is just the distance between the center of masses of the objects. And in this case, that's just the radius of the Earth. And this negative sign here means that the force of gravity is attractive. It's always trying to pull two bodies closer together. Now this particular combination is so common that it actually gets a name of its own, and that is little g, or the acceleration due to gravity at the surface of the Earth. Now, because all of these things are constant, the radius of the Earth, the mass of the Earth, and the universal gravitational constant, g at the surface of the Earth is also constant, and it has a value of 9.8 meters per second squared. Note that the unit here is a unit of acceleration. Now this should also make sense because if we go back to our friend Newton, we know that he said in his second law, force equals mass times acceleration. So the force due to gravity is the mass on the object times acceleration, and so in this case the acceleration is just given by g, and again, negative means that it's going to be directed downwards. So if we go back to our work equation, force times displacement, we said the displacement is the height, and then the force is the mass times the acceleration, so that's going to be m times little g. So we know that this work is equal to mgh. So if an object is starting here, height h, we know that if we drop it, force of gravity is going to do work on it to bring it down to the surface of the Earth. And so we can say that the potential energy stored in this object, or the gravitational potential energy, is just equal to that amount of work that's going to be done, which is mgh. So that is the capacity for work to be done on this object by gravity. So let's go ahead and do an example. Say we have a cliff jumper who is standing at the top of a cliff, and this cliff happens to be 10 meters tall, and our cliff jumper has a mass of 75 kilograms. So as she is standing at the top of this cliff, what is her gravitational potential energy? Well, we can use this equation to solve for that. So we know that her mass is 75 kilograms. The acceleration due to gravity is 9.8 meters per second squared, and her height is 10 meters above the surface of the Earth. So if you multiply this out, you'll find that 7,350 kilograms meters squared per second squared. Now this unit is kind of a mouthful, so there's actually an equivalent unit that we can use that's just called a joule. So 7,350 joules is her gravitational potential energy standing at the top of the cliff. Okay, so say our intrepid cliff jumper decides to actually go ahead and take the jump, and when she enters the water, what is her gravitational potential energy going to be now? Well, we can go ahead and use the same equation again, except this time now we know that her height is 0, and since we're multiplying by 0, her gravitational potential energy at the surface of the Earth is 0. So what happened to all of that potential energy that she had at the top? Well, as she fell, that gravitational potential energy was converted into kinetic energy. And we know that that is what work does. It changes kinetic energy, and so this work that gravity did changed her kinetic energy. And if we know the equation of her kinetic energy, which we do, we can actually solve for her velocity as she enters the water. And we do that just by setting her kinetic energy at the water equal to her gravitational potential energy at the top. So 1/2 mv squared equals mgh. And so one interesting thing that happens here is that these masses actually cancel out. So in fact, The velocity of someone entering the water does not depend at all on their mass. It's going to be the same velocity no matter what. So if you go ahead and solve this for velocity, you'll find that it's the square root of 2gh. And if we plug in the numbers we have, it's the square root of 2 times 9.8 meters per second squared times 10 meters. Can go ahead and check our units. We have meters squared per second squared, and then we're going to take a square root, so we'll end up with meters per second, which is good because that's the velocity. And this ends up actually being 14 meters per second if you do that math. So from a paper that was published in 2020, they took actual data of divers entering the water, which you can see here in a camera they set up, and they also measured their speed. And right here, this is showing the time after they hit the water. So at 0 was right when they hit the water, and the axis here is the speed, and you can actually see that coming from a 10-meter diving platform, they actually hit the water at just about 14 meters per second. So I'm not lying to you. Okay, so today we talked about gravitational potential energy. We found an expression for it, which is equal to mgh. We learned that this gravitational potential energy is the capacity for gravity to do work on an object. And we learned that this gravitational potential energy can be converted to kinetic energy. And we did some sample calculations. Thanks for watching, and I hope you learned a little bit of something.